covered something enough so I can comfortably announce test one. How do you like it? In the morning or in the afternoon? Announcement is done within a week, but you like it afternoon or morning? Afternoon. So it will be a Tuesday. Yes. Tuesday, so from what time to what time? 3 to 4 or 4 to 5? Do I teach them to do a test or we do a test I teach? Because where I would have stopped if I first teach is where the test would stop. The coverage would be where I would have stopped in the previous hour. So we start with the test, then I teach. Okay, so that is, today is 23, that would be not a fast or fast? Is this 30 or? So it will be on the 1st of October. Where are you laughing? So from 15 hours to 16 hours. I know because I just count January, February, March, April, May, June, July, August, September, November, December. Where did I go wrong? January, February, March, April, May, June, July, then it has to be August, then September, October, then November, then December. The top bits are 31, and then the bottom ones 30 or 28 or 29. So I don't need to. So the coverage of the test will be what we would have covered tomorrow. So it will be thorough. So last week, was it last week? Last week we said that if we have a field and we place in this field a conducting sphere, a couple of things happen. So if we get a sphere and we put it in our field given by E is equal to E naught K, E equal to E naught K, meaning that it is along the Z. Then we say that because we know the field originates from the positive to the negative, so this means that this lower part is predominantly positive, and this other part here is predominantly negative. By law of electrostatics, then the negative part will be able to attract. This is neutral at the beginning, but once you put it in an electric field, then you get the negatives being attracted to the southern surface of the southern surface of the sphere. Would have predominantly negative, and then the northern one will predominantly have positive charges. So now we no longer have field lines going through the sphere comfortably. and if they cannot go through comfortably, then we got a field that is now due to the newly arranged charges due to induction. So these induced charges will now create a distortion to the original, or what we call external so they will create a distortion. So assuming this is our Z, and then this is our equatorial plane on which we have the X and the Y, then we get a distortion, because now the field that will be in quotes within the sphere will be the same as moving from up to down. But we know we can't find electric field in energy in a conductor, an ideal conductor. It can only be outward, perpendicular to the surface of this field. So, but that's not the point. The point is that this field here may go scot-free, but this one will be as if it is coming from this positive here. This one also would appear as if it is coming from this positive here. And then on this other side, there is some distortion, but which is not so much. And then this would appear like it is coming from some positive here. And also this one will pretend to be coming from some positive there. This is minus Z. Some distortion, a little bit of distortion here, a little bit of distortion here, coming from those negatives here. This one also comes from these negatives here, and then this one comes off, enters to these negatives, terminates to these negatives, and then this other one gets distorted towards the sphere. So it gets distorted like that. And then for purposes of feeling at home or feeling comfortable, then we draw another field line which will go scot-free. 1700s here, around this place. This one will now get distorted inwards here, comes out there. Then we draw some other one just to make sure things are looking so sweet. So then we got our sphere, our conducting sphere, originally neutral, having these charges, and then if it is of radius capital R, capital R, then there are a couple of things that we can do. Using the boundary conditions, we can find out a couple of things that make us find the potential anywhere outside this sphere by using the couple of things that we have seen within the spherical symmetry. Are we comfortable with how the diagram looks and how it comes about? It comes from when you have your field lines covered and running up, and then you put in your sphere. The moment you put in your sphere, then you get this So now let's do the algebraic gymnastics. We already know the potential. The potential was given by ER theta being the same as summation from which field to which field? We got an expression for the so this is from L equal to what? What is L? L is just what? L is just what? So is it L or N?
It's L is equal to 0.
Okay. Up to N. Okay. So then we have AM R to the N plus Bn over I plus 1. And then we have PL cos theta. Once we have, so in this, it means that we can play around. R is the radius from the center here to wherever we want to go. So we have one scenario when we are just at the surface of the sphere, when R is equal to what will be V, and then we have when we are at the center, when R equal to 0, what do we got as the potential at the center? Any other place? And then we have the other case when we move as far away as possible. When R tends to infinity, what will be the potential? The moment we are able to analyze these key issues, then we would have finished our example. Never throw away things, because this box was in the trash. That's why now I am not complaining. Fred, never throw away things. So solution, we had written something on the solution, isn't it? That the surface of the sphere is an equipolar surface. Did we write that? Where did we end? This diagram. So now that we know how the diagram works, we know how it comes about, we know what takes place, so we do the solution of our example. And this solution is that the surface of the sphere, because it has the same radius, everywhere it's a sphere, so the radius is the same all through, so it has the same potential. So the surface of the sphere, Shirak, are you wondering whether I'm seeing negative charges together or what? Because you keep smiling like, when you see us. Grace, what happened today? They refused you to see you in front. All the spaces were quiet. Come here. Oh, here. Kadu. But Kadu now where would I put you? You are already in the middle. But how do you take me? I don't joke. that find where to be? I mean what I said. And I have a reason. Now these ones, I don't know what to do. They put a bag and flasks and then pretend that that's a positive charge. So Chibira will put those ones in the middle of them. There is a way it makes me have order. Extend what is attracting you? It's another. What is attracting you to Samantha? Do you remember Drude's motto? The time between two successive collisions is called relaxation time. It doesn't matter where you are seated, as long as the next point is a negative charge. Shut up. Doesn't matter where you sit, as long as the next point is a negative charge, you still become unfair. Seems you interchange that. For you, I know you want money. Shirat, please, let's not have influence. Where are you going? Where she is? She's still near the. See, when I mix you, you don't rumamonga. That's my objective. Like these ones, soon you see them rotating phones now that they are near each other. But I'll give them a chance, the benefit of doubt. Women, you've dodged me many times. I don't know whether any reason before I make my insinuations. Because I know how to read between the lines. That's really another. So the surface of the sphere is an equipoential surface. That equipoential surface, meaning that the potential is the same on the sphere. We may as well call it, we may as well make our life easy and call it potential zero. As well call it potential zero. Thus by similarity, the entire XY plane, the XY plane is the equatorial plane. The equatorial plane is at potential So we are saying that this XY plane, this plane here, which is holding the X and the Y, the X and the Y, is going to be at a potential zero. First of all, we say it is the same potential, which is an equipotential, but for purposes of comfortability, we even make it zero. And so, however, never get potential being zero as we move along the electric field that we are having. So, however, V does not go to zero at large Z. So as we move along of course, we have this constant electric field, so we can never have zero potential from E is equal to minus grad V. There will always be potential. So we can't have zero potential because we are having the electric field. In fact, far from the sphere, as we move far away from the sphere, in fact, I don't feel like rubbing my nice diagram. I use this one only.
Divide that.
I also divide this, but do I have to divide? Is it a must that I divide?
You can always use that one.
So in fact, you like arguing, just a small thing that this one wants to give it. So in fact, it is not in your damn head, so I don't need to bother. I don't need to bother the. So in fact, far from the sphere, the field is E naught K. And hence, okay, let it go. But it's on record, so don't worry. So, as we move far away from the, sorry, not far, along the field, so as we go along the Z, far away from this other point, so as we move far away from the sphere along the Z, then we would have the electric field immensity, or the field given by E naught K, and we know K is along the Z, so we can get if this is at any point, one point, and an angle theta here, in order to relate this R of the distance from the center to this point along the Z, that would be so as we move far away, then we have the potential tending towards minus E naught Z plus some constant C. Since V is equal to 0 in the equatorial plane, are you okay with this?
Me, I'm not okay.
Why? E is equal to E naught K. This one you are okay with it. Yes. Now if it is equal to E naught K, then we want to find the potential. So from E is equal to minus this, then V is equal to minus Kali by Kali Z. So if it is equal to minus Kali V by Kali Z, then you put your E naught. So when you put in E naught, that means it's a constant. When you differentiate, did I differentiate, or it should be integral? It should be integral. It should be integral E dz. So then it becomes minus E naught z, then plus the constant of integration. This one here is coming from this integration. So since V is equal to, we've already said that the equatorial plane here is, which is the xy plane, is an equipotential surface, and we are taking this potential to be 0. This is in the equatorial plane. The constant C must be 0. The constant C must be 0. Of course, if you are at the equatorial plane, V equal to 0, then 0 equal to this plus C, and at the equatorial plane, what would be the value of Z? 0. So that means the constant is 0. Accordingly, the boundary conditions for this problem, for this example, I don't like problems. For this example, the boundary conditions for this example are: 1, we have the potential being equal to 0. The potential equals to 0 when we are on the equatorial plane, and that means when we are on the surface of the sphere. And the surface of the sphere is the distance r from the center. So when the radius r of our sphere equals to the radius of the, when I say when the radius of our sphere means a spherical configuration or distribution of charge. 2, as we move far away from the, or as we move far away from the sphere, then we have the potential being the same as minus E naught z, and E naught z is the same as r cos theta. So this would be E naught r cos theta, and this is for when we have moved far away, or you can simply say as r tends to infinity. It's up to you to choose what you want to. So we are good. We've understood around the surface of the sphere. We've now studied a couple of boundary conditions, so we can fit this into our solution. And our solution is the, so we must fit these boundary conditions. We must fit these boundary conditions with a function of the form I don't like this. So we can say we must fit these boundary conditions within the solution, the spherical, the Laplace's solution of Laplace's equation in spherical form. I'm trying to make sure we got a solution, a general solution, isn't it? So if I say within a function of the form, then we write that solution. I'm just trying to make sure that it flows in your mind, not making it abstract. You have to read your mathematical methods in physics and any other mathematics that makes your life easy. So what did we call that solution? The solution on page, we came up with before this, so we said the general solution, yes, the general solution to Laplace's equation is a linear combination, then we made the equation 11. So we should say must fit within the general solution to Laplace's equation in spherical coordinates. Within the general solution to Laplace's equation in spherical coordinates. I don't like the way Griffith does stuff. So it's like we are going to attack the problem. How do you attack the problem? That language is not good. Then you attack. Me, I'm doing an example. I don't want it to be a problem. So the thing was saying in the function of the form, but that function we are talking about is the general solution to Laplace's equation in spherical coordinates, and that was the same as Vr theta being equal to the summation. So this general solution is Vr theta equal to summation L equal to 0 up to infinity E nu ALRL plus BN over RL plus 1. Then they change the polynomials. So the first condition, if we substitute in the first condition, which says that the potential is 0 when we are at R, then now our V, the R is equal to R, theta, would be the same as 0, and it yields our 0 equal to, so we put in the, where there is small r we put on,
the summation, last time you said it's from L is equal to 0 to N.
I didn't say, you say.
You're right.
And I didn't care. But what is in the notes is that you are from L equal to 0 up to infinity. expected you to tell me what you are seeing in the note. True or false? And you are busy telling me up to n. And there's no, if you remember what n was, and why we said that we cannot have n equal to 0, if you remember, n was the number of, this is the order of the polynomial, but the L is the order of the polynomial, but n was the number of the field lines. So you couldn't start from 0. Neither can you have the order of the polynomial going up to the number of field lines. How? Are we okay? Like I said, I'm now not going to trust you at all. When I'm doing my stuff, I will be fixing myself on what I want. But I also always want to give you freedom to mess up yourselves. After all, the notes are very and are clearly put. Any other query? Good. So now we put in the R. The whole thing we said is 0. So here we will be having AL, then we would have R to the L plus BL, and then over the capital R, L plus 1, and this should equal to 0. And or we can multiply by L to the L plus 1 throughout, and then equal to 0. That will make us remain with the, this will go there and becomes 2L plus 1. So AL 2L plus 1 BL. And then we can have the BL being the same as minus AL. Then R to the 2L plus 1. Hence, now that we got BL, in terms of AL, we can rewrite our general solution, our potential expression in terms of the A's. I'm just doing algebraic gymnastics, Chimira. There's nothing physics that needs to be explained. I'm just trying to put in the at the surface of the equatorial surface, R is equal to capital R, the radius of the sphere, and then the potential at that point, we said it is an equipotential surface, almost all through the sphere, but especially at the XY plane, and then it becomes 0 equal to this we put in R, and because we are at the surface of the sphere, we don't need to hustle with summing up. We are not going nowhere, we are just like at the origin, because we are at the equatorial plane. So our potential now would be the same as summation L equal to 0 up to infinity. And then we put, where there is BL, we put minus AL out of the 2L plus 1. So we can put AL outside. And then we have remain with RL in here. And then we have the minus R to the 2L plus 1. And then we divide by the R to the L plus 1, and then we multiply by the Legendre polynomials. So that was the condition 1. At the surface, when we have the R equaling to the radius of the sphere. How about now the condition 2 as we move away, far away from the sphere? As R tends to infinity, then the second term, this one here, if you blow up R, even the power next to the L plus 1, when it is already becoming infinity, this whole term becomes 0. So the second term in parentheses is negative. So in other words, we have this R to the 2L plus 1 over the R, L plus 1 tending to 0. And therefore, the condition 2 requires that, remember our condition 2 says that the potential as you move far away from the sphere, you differentiate the electric field intensity to get the potential at any point as you move away from the sphere. That was our condition 2. Condition 1 was that V is equal to 0 at R equal to R, and then V tended to E naught Z, is it E naught Z or R cos theta? Cos theta at R tending to infinity. So, and therefore, condition 2, above means that, what we had written some time ago? Above requires that summation as L tends to, L from 0 to infinity, AL R to the L, PL cos theta equals to minus E naught R cos theta. The constant was equal to 0, so there is a minus. So if R tends to infinity, the second term has disappeared. So if the second term disappears, this one, as we go towards infinity, is equal to minus R E naught R cos theta, and then this other side will be the summation of this AL. What is surviving is only this term, which is why we have AL, R to the L, then PL cos theta, equaling to the potential that we derived from integrating the electric field far away from the sphere. So since PL or P1 cos theta is equal, the first polynomial was equal to 1. P1x or P1 cos theta was equal to. So we can start from 1, see what happens when n equal to 1, and then we can then get something out of that. So since PL cos theta, since P1 cos theta, it looks like PL. So since P1 cos theta equals cos theta, this is for L equal to 1. We see by inspection that see by inspection that A1 would equal to, A1 would equal to, if we put L equal to 1, this would be A1 R cos theta equaling to minus E naught R cos theta. So the R's would go, the cosines would go, A1 would equal to, negative E naught. For L, for the order of the polynomial 1, if we put it in here, then this would be, we're summing up to 1, so no big deal. Don't need to sum anymore. So this would be A1, R up to the 1, which is R. P1 cos theta is cos theta, so we have A1 R cos theta equaling to minus E naught R cos. The cos's will go, the R's will go, A1 will equal to E naught. And once that is the case, all the other ALOs, yes? Pardon? Try to put, you want to put the order 0 and then add also the 1. What do you get? What is B0 cos theta?
1.
And then you'll be having 1 times, this is 1, this is A naught, and then you add on, why am I wasting my time? This is the problem I faced all the time. The moment I want to make sure everything is understood step by step, people introduce their own problems. Yes?
Let's say now at the potential, which was the summation from L is equal to A, say there's a number of field planes, and you cannot have 0 on the field.
I just want to be sure when you insist. The general solution for on page 59 on Mwere, which we got for the general solution to Laplace's equation in spherical coordinates is summation L equal to 0 up to infinity. That's the general solution I wrote at the beginning, and you were telling me it is up to n. And I didn't care because I hadn't even touched my notes. I knew when I touched my notes I would get what I want. And you have it in the notes. And you are supposed, that's why I said within, to fit within the function we remove it. We fit within the general solution to Laplace's equation in spherical coordinates. The example is beyond where it is in Griffith, in the reference book. Just the way it is here, the way I'm chopping it here is the way it is in the book. So you can verify whatever it is there. So allow me to chop my thing. All other ALOs are equal to 0. How? Conduct your mathematics. So that's That's the general solution. That's the general solution, meaning that we started well by making sure that we call it a general solution to the Laplacian equation in spherical coordinates. VR theta would equal to A1 E nu R minus R cubed over R squared, then PL cos theta. Substituting for A1, this, no, it is a 1, L equal to 1, so this is a 1. I hope in the notes it is clearly shown. So that means that substituting for, we already said K1 equal to E naught and P1 cos theta equals cos theta. So substituting for A1, which we said is equal to minus E naught, and P1 cos theta, which we said is equal to cos theta, from above yields our equation now becomes, our general solution becomes VR theta is equal to minus E naught E nu R minus R cubed over R squared, then cos theta. This is the potential everywhere outside the sphere. So the steps, if you remember, is the first step is to find out how the field is affected. Is it affected, or is it the field that affects the sphere, or how the sphere affects the field?
The sphere is affected by the field.
What happens to the sphere? Just apart from the effects on the sphere are not really significant like the way we see the field being distorted. So the effects of the sphere on the field, then we get that displacement of the positive charges to the top or northern sphere surface, and then the negatives to the southern surface. And then once that happens, distortion takes place. Once distortion takes place, we assume the surface of the sphere to be an equipotential surface, and we set this potential that is being the same along the equatorial plane to be 0. And once it is 0, that means at the r equal to r, the radius of the sphere, we get the potential being 0. That's the first condition, v equal to 0 at r equal to r. And then we try to find out, how about if we move away from the sphere, far away from the sphere, what happens? This would be dependent on the field that we place this, in which we place this sphere. And this field is E naught k. It's along the z. That means we can use the E minus grad v in order to find the potential anywhere within this field as we move along the z. And that means the v will be telling minus E naught z or r cos theta plus the constant of integration. But if we take the conditions that at the beginning, when we got z equal to 0, then we have the potential at that point also being 0 at the equator, that is the xy plane. If the potential is 0 and z is 0, then our constant of integration will be 0. The rest is like gymnastics. In order to find the constants a and b, so we put in r equal to capital R, we first get the constant here. Then we substitute in the general solution, we get the expression in terms of the constant K. Then we say, anyhow, we can't grab everything, we take for the order 1. And then when we take for the order 1, we get A1 equal to E naught, and then eventually get the P1 plus theta being cast theta. We put in everything, we get this. And this has two components. This first part here, which is E minus E naught R cos theta, is what we say is far away, because that's the part which is far away from the sphere. So it's like the external field, the potential outside there. Then this one, which constitutes the radius of the sphere, will be around within the surface. Within, and remember, we can find potential within a character, but it is constant for a given point, 2 points. The potential difference will be constant. So we can just trying to sound nice. Now that we got the potential, we can extract information from this potential with the contribution from the outside, and then within the sphere. And then we can also find the charge density. What would be the surface charge density for this sphere? As we look at, and you can find other things if you want, as long as they are related to the potential and the electric field density in which we place the sphere. You don't need to cram, you just need to know what is going on. Sphere is put in the field, gets induced. Its induced electric field causes a distortion around the XY plane. The potential is zero, the rest is just flow. In this solution here, the first term, there are 2 terms. So the first term, which is minus E naught R cos theta, is due to the external field. Is due to the external field in which we placed the sphere. This whole place, we placed it in minus E naught theta. And the potential emanating from this is the same as minus E naught R cos theta. So this is due to the external field. The contribution attributable to the induced charge, this one here is given by the second term. It's given by the second term. And the second term is the same as positive E naught R cubed over R squared, then cos theta. If we wish to understand the charge that has been induced on this surface of the remember, it has, part of it has gone up, part of it has gone down. It's not uniformly distributed on the sphere. So we can safely take what we call the charge density. So if we wish to know the induced charge, to know charge, which is not easy to find the induced charge. We can only try to make it populated around the sphere. So we talk of induced charge density. We can find it from what is surface charge density equal to? Yes, well. E D dot D dot N. So where are we going to get the D from here? Can you express it in terms of what we got?
No.
So D is in terms, we got electric field density. So what would be D in terms of electric field density? So we placed the field, the sphere in space with the field E naught, meaning that the permittivity of that free space is epsilon naught. So you say it is, come again, it is so D, so epsilon naught. So you said Khalid by? This is very interesting. You said it is D dot D dot N. So what is N? So this is minus epsilon naught Kali V Kali R, and we shall concentrate on, since we are talking about surface charge density, where do we be? Where do we be? We are in a differential in respect to R, so since we are talking about surface charge density, where would we be? At R equal to? At the surface of the sphere. The rest is? So this would be the same as we put the V, this whole V here, and then when we do the differentiation, we get epsilon naught E, minus goes on, we get E naught in 1 plus 2R cubed over R small cubed cos theta. This is at R equal to R. Therefore, sigma theta will be equal to 3 epsilon naught E naught plus theta. Don't want to make any mistake. That's why you see me trying to make sure that I keep my eyes on the where is Jeremy? Mine. Where is Jeremy? I warned you last time that you are distracting him, so now he's not even there. Eh? Parasita is what? He sent you a message. Why did you read? We can go on. We have the potential. We can also find. Why are we talking about the sigma R, for example? why are we having sigma theta? Why are we talking about, when we talk of, why aren't we having sigma r and sigma theta? Because of what?
At the surface. And the surface, the protection is invisible state.
When we talk of the surface, we are sure that the R will be constant, some value. So we talk about, we can scan through the whole angle. For example, this equatorial plane, we can scan through that plane that slices through the web in the sphere. That plane can scan through all over the surface to see what will be the surface charge density. But the radius is bulging, so you can't be moving away from the center of the sphere and then top of the surface charge density. The surface is changing. If it is bulging, it is becoming bigger and bigger and bigger. So the surface is changing, and then you are looking for the, if you take R to be a contributing factor, then you can't get a particular. That's why here we are sticking to be at the surface and stick to that surface of the sphere that we got. Otherwise, we wouldn't do much. So the components of the electric field intensity, where we get a potential, we get electric field intensity. Where we get electric field intensity, we can get potential. So the components of the electric field intensity, components of the electric field intensity are, we have here, this is the radio or the R component of the Kali V by Kali R from minus 1 V equal to E naught E no 1 plus 2 R cubed over R squared cos theta. And then the angular component E theta would be the same as minus 1 over R. This is from polar coordinates. From the electric dipole we had in electricity and magnetism. This will be equal to E naught E mu 1 minus R cubed over R cubed small, then sine theta. This is also derived in mathematics, since our E is equal to minus grad V. So note that, or remember that, if you go to the formulas or the identities, remember that in spherical coordinates, the gradient of Pareda grad V is equal to Kali V by Kali R roof plus 1 over R, Kali V by Kali theta roof plus 1 over R sine theta, Kali V by Kali theta, phi, this is phi. Then phi roof. It is from this that if you took the divergence of the gradient of Pareda, then you would end up with the expression in Laplace's equation in spherical planets. Remember, yes.
The second one, are we differentiating this with
It is there. Don't make life hard. This is R what? R cube.
Yes,
A, yes. I told you don't trick me like those secondary kids. You have filled up the body with X tube for you, I guess. Yeah. You don't know how it feels. Even if you teach, you don't care because you are not really judged by how the teacher you are, maybe by how you talk. But these ones who have done school practice will tell you, you have filled the board and some fool who has just been, when you have been keen, you have been seeing him just drawing some things on the cover of the book. They say, excuse me, sir, is that X cubed or X squared? And then you come on the board, you are like, no, me, I used to be clear. I don't have time to waste. If you want to ask, say, online this or this part of the board, or step this, you can't tell me, is that X cubed or how? Where do I begin from? So you need to be fair and tell me that no, you have that second part, the angular component is supposed to be different. Have that confidence. I'm not going to kill you. You have written squared instead. I mean, R. You are still differentiating with respect to R when it's supposed to be with respect to theta. And then you say that when you differentiate that one becomes R cubed. I have it in the notes. I won't quarrel. I'll just confirm by looking. Neither do I want to waste time that I'm talking differentiation with you as if I'm your math teacher. So this is our, you can see, this example is to show you how do we apply the one of where we ended up with the Fourier series. And eventually got to move in on the finding the final potential. Did not come out because it's like we just concocted something. Two electrodes dominated by an electrode that kept at V naught and zeros. Are you on Mwere or on WhatsApp? So what would you be keying in on Mwere? Once you are notes, you keep looking at the notes. But he's just busy typing. How can you type? Even the parasita keeps typing. How do you type?
Feeling the phone.
She's feeling the phone. From the beginning. I would be lucky. One student tried to do for me that in a project, but he did not really make it. They say, I don't know, some banks and some embassies have a machine which cuts off the network. And so, I think including the presidential, whatever, not convoy as such, but even when they are walking around within a function, everyone is off. So, I want to buy that. I wanted to buy that before COVID. And when COVID came, things became tough for me. Those days I used to put the phones, that sink there. I put, I think, 4 phones. The one in the lecture theater. It had dirty water, so I would just get it and throw it there. I'm teaching somebody is busy receiving calls. He's doing this. So I say, you bring it. Then I put in water. And sometimes I will give them advice. You go soak it in rice, it will get better. But now that they say online and here blended, when I'm teaching calculations equation. Do you feel comfortable when you are saying that we are here? We are how? How does that happen? So I don't know, but I think I should bring back my old days. Come with the bucket with very dirty water. And we agreed that during lectures, it was on the where it was clear. No phones should be off during lectures. Those days I used to use Mwere, but class time is class time. And notes of a particular lecture used to be already active when we have finished the lecture. So you can't say I'm looking at the notes from where. And also I had made them unprintable. So you couldn't print and then just come and keep sitting like a cabbage like this. And appreciate me and then go away. So I had made them not to be printable. All of them. No, they are printable now. So we do another, or I give it as an exercise, or we do another, or we now move on to go to Srimika. Okay, another example. I will do, but you'll do. I will do, no problem, but you will do. On the 1st of October.
Not everything will happen.
So, if I say, will you do? No, do. I'll do. So the electric sphere, the other one, this one was conducting. So how about if it is a electric sphere in a uniform electric field? In a uniform electric field. Consider the calculation of the potential. Consider the calculation of the potential at any point. At any point for the case in which the dielectric sphere of radius small a and permittivity epsilon is placed in a uniform electric field. Is placed in a uniform electric field. And this electric field is more or less like the one we got, E equal to E naught K, which exists in free space. Which exists in free space, whose permittivity is epsilon naught. Okay, so the difference is that the other one was a conducting sphere. Induction took place, northern surface became negatively charged, became positively charged, the southern surface became negatively charged. This is a dielectric. So here, the potential would be equal to minus E naught Z, which is the same as minus E naught R cos theta. Cos theta is the P1 cos theta, the second polynomial, so this would be minus E naught R, so this is P1 cos theta. The total potential VR theta, the total potential VR theta must satisfy the following, BCs, the following boundary conditions. One, the VR theta would tend to be naught for when you go positive infinity. Then V2, VR theta must be continuous, The potential should be continuous at the surface of the dielectric sphere. 3, VR theta, our potential, must be finite. Should be measurable at the radius equal to 0. At the center of the dielectric sphere, you should be able to find some value for this potential. And then finally 4, since the sphere is dielectric and it is having the permittivity epsilon, and it is placed within a medium which is having the permittivity epsilon naught, which is free space, that means the moment you want to cross from the sphere, dielectric sphere, outwardly, means that you will have crossed the boundary. Meaning that we can apply the boundary conditions we got for the electric field energy, especially, because that's where we get the potential. So the fourth one is that the normal component of the electric displacement vector, denoted by D, must be canvas. At the interface. The interface is at R equal to A. So we got these conditions. We know the theory behind a dielectric placed in an electric field. We say that there would be bound charges which would be attracted on either side. If it is placed within a field, assuming there are two plates, the positive plate will have a negative bound charge, bound to be there because of the positive charge on the plate, and then the other negative plate will have a positive bound charge, bound to be there because of the presence of the negative charge. And then here we are saying that at the interface, the electric displacement would be just the normal, its normal component would be just going through straight. And of course here we take it as being radial, because the radius of the sphere is perpendicular to the circumference of the surface, if you want to take it in that form. So we are dealing with a sphere, so we need to recall the general solution to Laplace's equation in spherical coordinates. So this will be the same as the summation. Don't tell me n again. L equal to 0 up to infinity. We have the AL R to the L plus DL over R to the L plus 1. Then the polynomials. The moment we got this, then we do the analysis. And the analysis are that in order to satisfy condition 1, this one here, in order to satisfy condition 1, the solution exterior to the surface, that is the potential exterior. The solution here will mean this potential here. Exterior to the surface, to the sphere, exterior to the sphere at R tending to be far away from the radius of that must be of the form V exterior or external, V external, R at theta being the same as V naught, the one which is at, as you tend far away positive, then plus what we can come up with. So this would be PL R to the minus L plus 1, then PL cos theta. While the solution, I'm not going to do math again. While the solution in area, to the surface, that is inside the surface or sphere? immediate to the sphere, that is when you are spinning within the sphere less than the radius of the directed sphere, must be by the condition. The condition that says that is condition which one? Must be by condition 3. Inside the sphere is when you are having at the center of the sphere, you are well inside the sphere. Between 0 and A, that is a range that we need to be particular. So by condition 3, and B of the form, I don't know whether this fits there, so this will be, I put it this way, for clarity. B of the form V immediate of the sphere, R of theta being the same as the V naught. I have dropped the conditions, but the V naught is when you are moving to infinity or positive to infinity as you move along the field. So this would be plus this other one, so plus summation L equal to 0 up to infinity. Then the other one was BL, here we have AL, R up to the L was L. I've just separated these two. This one here, this part here is the exterior from the previous example. This other second term gives you the immediate because of the peculiarity of the radius of the capital R which we have. So I have written V naught, which is the potential that will be felt as you go, that first condition as you go positive infinity, plus for the external, plus this part here, which is summation A equal to 0 BL. BL, then this one I put it in the same line up, become minus N plus 1, RI plus 1. Yes, the PL is missing here. The problem is when I'm writing, I'm hurrying to make sure I explain the thing. So this is the other term. Now here, the nano is when we take this part. And the rest is derived in master. So according to condition 2, condition 2 is R equal to, that should be R equal to A, I guess. And this should be continuous. The potential should be continuous across the interface. So according to condition 2, these two solutions must be equal if there is continuity. There is continuity. What is before the interface within the dielectric should be equal to just outside the sphere, which is within the free space. So that means the V immediate and V exterior should be equal. So according to to these two solutions, that is immediate and immediate must be equal at the interface or at the interface. Yes, at the interface. At the surface of the electric sphere. Thus, we are saying that V exterior R theta. So the external one at R equal to A is equal to the internal one at R equal to A. So where there is small r, we have put A, and this would imply that summation, this is the exterior, if they are equal, the V naughts would cancel. So the summation of dl is L equal to 0 up to infinity, and then we have the dl. R is now A minus L plus 1. The dl cos theta are both sides, they also cancel out. So, but if you don't want to do that at the beginning, for purposes of kilometry, this would be the same as summation. All L, so you can still go up to infinity. AL, this is R is now A, the R, then PL cos theta. The summing, you are summing, so no big deal. You got PL cos theta, PL cos theta, no big deal. So this would imply that we have the BLA, so our AL would be equal to BL A minus 12 plus 1. So I got a constant A in terms of B. So I can put it in the solution to Laplace's equation in spherical coordinates and run around to get the potential. Yes.
On the right hand side of the expression, where we have like summation of AL, A power, supposed to be A power L.
Yes. Thanks. Now you are cooperating. Fred, up to now you can't see bad things. So we have this one as equation 1. You are waiting to get the Holy Spirit that shows you the wrong things. You may wait after first you will have gotten the courage. So can I be quick? So since the Legendre polynomials, what did we say was the spelling like this? Or the E? This one.
There's an N missing.
It is? Okay, so but everything else was okay.
Yes.
So since the Legendre polynomials are linearly independent, are linearly independent. The coefficients PL of the PL cos theta must be equal. If they are linear independent, whatever is the coefficient to this should be the one to be equal. So much as I said, much as I cancel them, but the idea behind is that the coefficients should be equal to, should be the same. So if they are equal, if we take, I told you this equation, you need it every time in spherical coordinates. In spherical coordinates, not long ago, we agreed that the E, so this is E external R, the R component would be the same as minus V external by kali R. And once we do the chopping, we get A external this would imply that E external R component would be the same as E naught PL cos theta, then plus summation all over L, so it's the same as saying L equals up to infinity or any other limits you want to take. L plus 1 and then dl r to the minus L plus 2 L cos theta. I have no time to waste this. For Inano, E Inano, the other component will be the same as minus kali V Inano by kali R, implying that E Inano would be the same as minus, E naught PL cos theta minus summation over the L in room L R to the L minus 1 PL cos theta. But the last condition, which was condition 4, we said that there is continuity of the normal component of the electric displacement vector across the interface at r equals small a. And we also know that d is the same as epsilon e. So in order to satisfy the condition 4, in order to satisfy boundary condition 4, we must have d1n equaling to d2n, where 1 is the medium one, which is the dielectric sphere, and 2 is the So this implies that epsilon in medium 1, we take the medium to have, so we got the, what did we say was the dielectric, the permittivity of the dielectric sphere? Epsilon 1 or epsilon? We go back, make it epsilon 1, because we're going to use epsilon 1 for some good time now. In the question, sort of, it should be epsilon 1. Let's say, it's just epsilon, but let's make it, correct it to epsilon 1. An example, just at the beginning. Sphere already has small a and permittivity epsilon 1. So we shall have that epsilon 1, sorry, epsilon naught, then the interior, I mean the exterior, because that's where the electric sphere is. So this would be E exterior R. This is at the surface of the electric sphere, which is the interface, should be equal to the V2, which is the, now inside the dielectric sphere, so it will be epsilon 1, E interior R at the surface of the sphere. Are you tired? Well, the other group, the other student, I think they are second year, very many, but suppose being small room. So they are having a test, and this example is becoming sweeter and sweeter, but it needs us when we are fresh, when we are beaten tomorrow at 3, and then we